Hello friends, welcome to my second lecture on graphical method. We will discuss some exceptional cases here. We will discuss the case earlier, the examples that we discussed there we had unique solution. Now we will discuss the cases where there are infinite number of feasible solutions, then a case where there is no solution, and then a case where unbounded solution we have. Okay. So, let us first consider the case where there are infinite number of feasible solutions. Let us consider this linear programming problem z equal to 100 x 1 plus 40 x 2. We have to maximize this expression subject to the constraints 10 x 1 plus 4 x 2 equal to less than or equal to 2000, 3 x 1 plus 2 x 2 less than or equal to 900, 6 x 1 plus 12 x 2 less than or equal to 300, and the non-negative restrictions x 1 x 2 greater than or equal to 0. Now, we will determine the problem is to determine x 1 x 2 which maximizes z equal to 100 x 1 plus 40 x 2. Okay. So, let us draw the straight lines 10 x 1 plus 4 x 2 equal to 2000. So, 10 x 1 plus 4 x 2 equal to 10,000, this is your line 2. Okay. Line 2 is 10 x 1 plus 4 x 2 equal to 2000. So, this line is 10 x 1 plus 4 x 2 equal to 2000. 3 x 1 plus 2 x 2 equal to 900. So, this line, okay, this line is 3 x 1 plus 2 x 2 equal to 900, and the fourth one is 6 x 1 plus 12 x 2 equal to 3000. So, this line, okay, this line is 6 x 1 plus 12 x 2 equal to 3000. Okay. So, we have these constants 10 x 1 plus 4 x 2 less than or equal to 2000, 3 x 1 plus 2 x 2 less than or equal to 900, 6 x 1 plus 12 x 2 less than or equal to 3000. Also, x non-negative restrictions x 1 x 2 greater than or equal to 0. Now, let us see what is the region which is the feasible region here. So, you can see this region. Okay, this region is the feasible region here. Okay. In this case, for this region 10 x 1 plus 4 x 2 is less than or equal to 2000, 3 x 1 plus 2 x 2 is less than or equal to 900, 6 x 1 plus 12 x 2 is less than or equal to 3000, and also x 1 is greater than or equal to 0, x 2 is greater than or equal to 0. So, the solution space satisfying in equations 2, 3 and 4 and meeting the non-negativity restrictions 4, okay, non-negativity restrictions 5, okay, and this one, this is non-negativity restrictions, there is no equation number here, non-negative restrictions is shown shaded in this figure. Okay. Now, let us note that this condition 3, okay, is a redundant condition because it does not affect the solution space. Let us see how it does not affect this line. You can see this line. This line is not affecting the solution space. It is a redundant condition. Okay. This region is obtained as a result of this line 6 x 1 plus 12 x 2 equal to 3000 if you consider this line and you consider this line, okay, 10 x 1 plus 4 x 2 equal to 2000. So, we as a result of this condition, this one and this one, okay, we are getting this condition 3 x 1 plus 2 x 2 equal to 900, although for this region 3 x 1 plus 2 x 2 less than or equal to 900 is valid, but this condition is not being used here, okay, to obtain this solution space. So, this is a redundant constant, okay, This is a redundant constant as it does not affect the solution space. The vertices of the convex region OA, BCO. Okay, let us look at the vertices. So, this O, A, B, C, O. Okay, OA, BCO are the coordinates of O, A, B, C can be easily obtained. Okay. So, they are 0, 0, 200, 0, 125, 187.5, 0, 250, and the value of the objective function z at the point 0, 0 is 0, at the point A it is 20,000, at the point B it is 20,000 again, at the point C it is 10,000. So, we can see the maximum value of z occurs at two vertices A and B, okay, at A as well as B at B, okay, at this and this we get the same value of z, okay, and so the value of z is same along this line, and therefore, so there are infinitely many solutions. So, thus the maximum value of z occurs at two vertices A and B. Any point on the line joining A and B will also give the same maximum value of z. Okay. Thus, there are infinite number of feasible solutions, okay, which yield the same maximum value of z. Okay. So, this is an example on infinite number of feasible solutions. Now, solve by graphical method the LPP, this one. Let us take this case now, z equal to 5 x 1 plus 6 x 2, and there are these constants, okay, and non-negative restrictions again are x 1 x 2 greater than or equal to 0 each. Now, again let us draw the lines x 1 plus x 2 equal to 50. So, this is line x 1 plus x 2 equal to 50, x 1 plus x 2 equal to 50, okay, and the second line is x 1 plus 2 x 2 equal to 40. So, we have x 1 plus 2 x 2, okay, this line is, okay, this one, this line, it is x 1 plus 2 x 2 equal to 40. On x 1 it intersects at the point 40, 0, and on x 2 axis it intersects at the point 0 to 0 20, okay, here. And the third line is 3 x 1 plus 4 x 2, 3 x 1 plus 4 x 2 equal to 100. Okay. So, 3 x 1 plus 4 x 2 equal to 100 is this line, this one, okay, 3 x 1 plus 4 x 2 equal to 100. On x 2 it intersects at the point 0, 25, on x 1 axis it intersects at the point 100 by 3 comma 0. Okay. So, now we can see we have the condition that x 1 plus x 2 is greater than or equal to 50 here. Okay. So, the region which satisfies x 1 plus x 2 greater than or equal to 50 is this one, this region, okay, this region. In this region x 1 plus x 2 is greater than or equal to 50. Now, the other two equations are x 1 plus 2 x 2 less than or equal to 40, okay, and 3 x 1 plus 4 x 2 less than or equal to 100. So, they give us this region, okay, this one, this region. Now, we have to find the solution. Okay. No values of x 1 and x 2 can satisfy the constants given, because the constant x 1 plus x 2 greater than or equal to 50 says x 1 x 2 should belong to this region, but the other two conditions says x 1 x 2 can belong to must belong to this region, and they are not there is nothing common in the two regions, okay, they are disjoint. So, no values of x 1 x 2 can be obtained for this problem, and therefore, there is no solution to this problem. So, since we see that there exists no value of x 1 x 2 that simultaneously satisfy all the constants and the non-negative restrictions, the given problem has no solution, no feasible solution. So, this is a problem on no solution. Now, let us take an example of an unbounded solution. Suppose we have to solve this LPP z equal to 3 x 1 plus 2 x 2, the constants are x 1 minus x 2 less than or equal to 1, x1 plus x2 greater than or equal to 3 and x1 x2 are non-negative, then what shall we have? Okay. So, let us draw again the line x1 minus x2 equal to 1 and x1 plus x2 equal to 3. So, this is x1 minus x2 equal to 1, okay. x1 minus x2 equal to 1 and this is x1 plus x2 equal to 3, okay. And the inequalities are x1 minus x2 less than or equal to greater than x1 minus x2 less than or equal to 1. So, x1 minus x2 less than or equal to 1 is this region, okay, this region, that is x1 minus x2 equal to 1, x1 minus x2 equal to 1. Okay. I mean here x1 minus x2 is greater than or equal to 1 in this part, okay, and x1 plus x2 is greater than or equal to x1 minus x2 is greater than, no, we have x1 minus x2 less than or equal to 1, okay. Yeah. So, this part, for this part x1 minus x2 is less than or equal to 1 above this line, okay. All the part above x1 minus x2, okay, equal to 1 satisfies the inequality x1 minus x2 less than or equal to 1, because 0 0 point, okay, for 0 0 point x1 is 0, x2 is 0 and 0 is less than or equal to 1. So, this 0 lies above this line. So, this portion, okay, this entire portion satisfies x1 minus x2 less than or equal to 1 and we have x1 plus x2 greater than or equal to 3. So, x1 plus x2 greater than or equal to 3 is this region, okay, because 0 0 for 0 0 x1 plus x2 less than or equal to 3 0 0 lies here. So, this region, okay, this region is common and also we have x1 greater than or equal to 0, x2 greater than or equal to 0. So, this region is the region satisfied by all the constants and non-negative restrictions, okay. Now, this is unbounded region we can see, okay. So, if you consider the profit method or iso cost method, what you do is you draw the line 3 x1 plus 2 x2 equal to 0, okay, because you have to maximize z equal to 3 x1 plus 2 x2. So, you can consider 3 x1 plus 2 x2 equal to 0 line which passes through the origin. So, this is the line, okay, this line 3 x1 plus 2 x2 equal to 0 we have. And then you go on drawing lines parallel to this line, okay. When you enter the feasible region, there is no point line which is at the farthest from the origin and passes through the passes through a vertex where which is the beyond which there is no other vertex of the region, because you go on drawing, okay. There are always some points, okay, which lie in the feasible region. So, there is no end to the set of parallel lines. We can go on drawing them, there is no end to that. So, proceeding step by the permission region is shaded in the figure which is unbounded. From the figure it is clear that dotted line through the origin representing z equal to 0 can be moved parallel to itself in the direction of z, increasing and still have some points in the permissible region. You can go on drawing, you will always have points in the permissible region which are there. So, there is no end to this sort of parallel lines. So, we can say that this problem has an unbounded solution. So, thus z can be made arbitrarily large, okay, and so the problem has no finite maximum value of z, and therefore, we say that it has an unbounded solution. Now, let us consider a basic solution. Suppose we have a system of equations A x equal to b, where there are m equations and n unknowns are there, okay, and we assume that number of unknowns are greater than the number of equations, n is greater than m, and we are given that rank of A equal to rank of the augmented matrix A B, that means the system has a solution, okay. So, and the rank of A equal to rank of A B is equal to m, that is none of the equations is redundant, okay. M is the number of equations and the rank of A is equal to rank of A B equal to m. So, none of the equations is redundant. A solution obtained by setting n minus. Now, since the rank is equal to m, rank of A equal to m, and the number of equations are m, and number of variables unknowns are n. Okay. So, n minus m variables are arbitrary. Let us, if we set them equal to 0, okay, then we will have m by m m equations and m unknowns. Okay. After setting n minus m variables to 0, that solution of that system is called as a basic solution, provided the determinant of the coefficients of the remaining m variables is not 0. So, after you have taken n minus m variables to 0, the remaining variables that you have, m variables, their coefficients, okay, the determinant of the coefficients of that those variables should be non-zero. Okay. Such m variables, now such m variables, any of them may be 0, are called basic variables, okay, and remaining n minus m 0 valued variables are called non-basic variables. So, the variables which we have taken as zeros, they are n minus m in number, they are called non-basic variables, and the other m variables, okay, are called as basic variables. Thus, for a solution to be basic, at least n minus m variables must be 0. So, n minus m variables are 0, and the m variables that we are going to determine, okay, some of them may be 0 there also. So, at least n minus m variables have to be 0. A solution in which the vectors associated to m variables are linearly independent and remaining n minus m variables are 0 is called a basic solution. Okay. So, now a solution in which the variables vectors associated to m variables are linearly independent means the determinant of the coefficients of these m variables, okay, is non-zero. That is the meaning of the linearly the vectors associated to m variables are linearly independent. That means the column vectors of the column vectors of the coefficients, okay, of the m variables, okay, they must be, those column vectors must be linearly independent, because that will provide that will ensure that determinant of the coefficient of the m variables is non-zero. Okay. So, let us consider this problem. For example, find the optimal basic feasible solution, okay, of the following LPP. So, we have z equal to 6 x 1 plus 2 x 2 plus 9. The constants are, the conditions are 3 x 1 plus x 2 plus x 3 equal to 6, x 1 plus 3 x 2 plus x 4 equal to 6, and we have x 1 x 2 x 3 x 4 greater than or equal to 0. So, we have to solve this system. This system is having two equations. Okay. This system is A x equal to b, where A is the matrix 2 by 4. So, 3 1 0 0, okay, x 1 x 2 x 3 x 4, and then we have 1 3 0 1, and x is x 1 x 2, b is 6 6, okay. X 1 x 2 x 3 x 4 are greater than or equal to 0. Now, so in matrix form, this is A x equal to b, A is 3 1 1 0 1 3 0 1, that is second row, x is x 1 x 2 x 3 x 4, b is 6 x x 6 6, b is 6 6. Now, here n is equal to 4, number of variables x are 4, they are x 1 x 2 x 3 x 4, and m number of equations are 2, okay, in those 4 variables. So, the basic solutions are obtained by taking n minus m, that is 4 minus 2 equal to 2 variables equal to 0. We can take 2 variables equal to 0 at a time, and therefore, out of 4 variables 2 can be taken to be equal to 0. Okay. So, we have 6 such possibilities. Okay. We have x 1, x 2, x 3, x 4. 4 variables are there, any 2 of them can be taken equal to 0. So, out of 4 we can take 2 variables to be any 2 variables to be 0, such cases will be, total number of cases will be 6. So, in 6 number of ways we can take out of 4 variables 2 variables to be equal to 0. Now, therefore, the problem can have at the most 6 basic solutions. which may be basic feasible solution also. Now, let us see how to obtain them. Okay. So, these solutions are computed as follows. We have in the first row we have x 1 x 2 as basic variables, non basic variables are x 3 x 4 which are being taken as 0. We have said that the non basic variables are those which are taken to be equal to 0. So, they are non basic variables are x 1 x 2. Equations now reduced to, you see we have these equations. Okay. So, we are taking x 3 x 4 equal to 0. So, x 1 3 x 1 plus x 2 equal to 6, 3 x 1 plus x 2 equal to 6, and we have x 1 plus 3 x 2 equal to 6. Okay. When we solve them, what we have is 2 x 1 minus 2 x 2 equal to 0. So, we get x 1 equal to x 2, and x 1 equal to x 2 means 4 x 1 equal to 6. Okay. 3 x 1 plus x 1 equal to 6. So, this gives x 1 equal to 3 by 2. So, we get x 1 equal to 3 by 2, x 2 equal to 3 by 2. So, we get x 1 equal to 3 by 2, x 2 equal to 3 by 2, x 3 equal to 0, x 4 equal to 0. Is it a basic feasible solution? Basic feasible solution means it should satisfy the criteria that x 1 x 2 must be non-negative. Okay. Because we have the condition that x 1 x 2 x 3 x 4 are all non-negative. So, x 1 x 2 must be non-negative. So, here we see that x 1 is 3 by 2, x 2 is 3 by 2. So, it is a basic feasible solution. Okay. And for this basic feasible solution, the value of z comes out to be z is equal to 6 x 1 plus 2 x 2 plus 9. So, 6 x 1 x 1 and x 2 here are same. So, 6 x 1 plus 2 x 1 8 x 1 plus 9 means 8 into 3 by 2 plus 9. So, that is equal to 21. Okay. Now, the other case could be we take x 1 x 3 as basic variables, we choose x 2 x 4 equal to 0, then we get these equations x 3 x 1 plus x 3 equal to 6 if we take x 2 x 4 equal to 0. X 2 is 0, x 4 is 0. Okay. So, x 2 equal to 0 reduces this equation to 3 x 1 plus x 3 equal to 6, x 2 x 4 equal to 0 gives x 1 equal to 6, and we therefore obtain this solution. X 1 equal to 6 gives you x 3 equal to 6 minus 18, that is minus 12. Okay. So, we get x 3 equal to minus 12. So, x 1 is 6, x 3 is minus 12, x 2 is 0, x 4 is 0. Okay. So, basic solution exists here, okay, but it is not basic feasible solution. It will be basic feasible solution only when x 1 and x 3 and x 2 x 4 are all non-negative. So, here x 3 is negative, therefore, it is not a basic feasible solution. Now, we then take x 2 x 3 equal to 0, and then x 2 x 3 are non-basic variables, x 1 x 4 are basic variables. The equations are 3 x 1 equal to 6, x 1 plus x 4 equal to 6. So, we get x 1 equal to 2, x 4 equal to 4. So, it is a basic feasible solution, and its value is here z equal to 6 x 1, 6 x 1 means 12 plus 4 x 2 sorry 2 x 2, 2 x 2 means no. Okay. So, x 2 is 0 here. Okay. So, 0 plus 9. So, we get z equal to 21. Okay, for this basic feasible solution, and when we take x 1 x 4 equal to 0 and x 2 x 3 are basic variables, then we get these equations, and the solution is then x 2 equal to 2, x 3 equal to 4, and so it is a basic feasible solution, and here z comes out to be equal to 6 x 1, x 1 is 0, x 2 is 2. So, 2 into 2 is 4, 4 plus 9 13. Okay. And here x 2 x 4 are basic variables, and then x 1 x 3 are non-basic variables. Equations are this, and then we get x 2 equal to 6 and we get x 4 equal to minus 12. So, since x 4 is negative, it is not a basic feasible solution. So, no. Okay. And so, basic feasible solution cannot exist. Now, here x 1 x 2 are zeros, x 3 x 4 are basic variables, we get x 3 equal to 6, x 4 equal to 6, and so it is a basic feasible solution, but z comes out to be equal to 6 x 1 plus 2 x 2, x 1 x 2 are zeros. So, z equal to 9. Okay. Now, we have to find the maximum value of z. So, maximum value of z is 21 and it occurs when x 1 is 3 by 2, x 2 is 3 by 2, x 3, x 4 are zeros, or when x 1 is 2, x 4 is 4, x 2 is 0, x 3 is 0. So, here we obtain two optimal basic feasible solutions, okay, of the problem, this one and this one, okay, and z is equal to 21. So, if we solve this LPP by graphical method, then we see that every point on the line segment joining 2 0, this to 2 0 and 3 by 2 3 by 2 gives basic feasible solution and optimal z equal to 21. So, in a LPP, a feasible solution which is also basic is called a basic feasible solution. In a linear programming problem, a feasible solution which is also basic is called a basic feasible solution. In other words, a feasible solution to a linear programming problem in which the vectors associated to non-zero variables, that is basic variables, are linearly independent. This we have seen earlier is called as a basic feasible solution. Okay. So, that is a must, because otherwise if they are not linearly independent, then the matrix, then the determinant of the coefficients of the non-zero variables will not be zero. The column vectors of the determinant of the matrix formed from the coefficients of the non-zero variables will not be non-singular, okay, if they are not linearly independent, and so determinant would be 0. So, then we will not call the feasible solution to be basic feasible solution, and the variables associated to basic feasible solution are called basic variables. So, this we have earlier also seen. So, that is the now if a basic feasible solution of a linear programming problem is said to be non-degenerate if none of the basic variables is 0. Okay. So, like we have got the non-basic basic feasible solution here. Okay. Here you can see this basic feasible solution. Okay. Here the basic variables x 1 and x 2 are both non-zero. Okay. So, it is a non-degenerate basic feasible solution, while this one here, okay, x 2 is 0. So, it is a it is not a basic non-degenerate basic feasible solution. A basic feasible solution of a LPP is said to be degenerate if at least one of the basic variables is 0. So, here we can see this is non-degenerate basic feasible solution, this one is non-degenerate BFS, and this is degenerate BFS. Because one of the variables basic variables is 0. Okay. So, that is the end of my lecture. Thank you very much for your attention.